Okay, so we're going to do a multiple linear regression. I'm going to walk you through an example, and I'm going to go back and forth between SPSS and the PowerPoint. We're going to create a predictive model for housing market around the University of Wisconsin. First, we're going to predict the sale amount of single and multifamily houses. So our dependent variable will be called sale amount. That's the variable name. Using the number of bedrooms, number of bathrooms, square footage of the house, and square footage of the lot on which the house is built. We're going to use 0.05 level of significance for all statistical tests. So here is our data set. This is the record, the sale amount, sale date, beds, baths, square foot of the home, square foot of the lot, the type, the build year, the town, and the university. Now, these are not value labeled, however, they are string variables. University is a constant because it's all University of Wisconsin. The town is also a constant because it's all Madison, Wisconsin. The build year is a scale variable, you can see by the little ruler. And single and multifamily label is not important, so we're not going to fool with it right now. So the first task is to provide descriptive statistics, the average, median, minimum, maximum, and standard deviation to describe the houses in Madison. Okay, so if I go to Analyze, Descriptive Statistics, and I come over to Descriptives, it asks for mean, median, min, max, and standard deviation. But if I go over here, I can see that I have mean, standard deviation, min, max, but no median. So I'm not going to use that one. I'm going to cancel that. Go back to Analyze, go to Descriptives, and go to Frequencies. And you can see that I have mean, median, come down here, minimum, maximum, standard deviation. Continue. I'm going to bring over sale amount, beds, shift, and get the rest of these. Okay, so I've got them all over, and I'm going to actually uncheck display frequency tables, or I'll get very long tables and say OK. And you can see I've done it already. Here are the descriptive statistics, and you can see I've put them in here. So now we're going to build a regression model to predict the sale amount of a house using all the predictors that we just talked about. And this is going to be referred to as the full model. Okay, let's go to Analyze, Regression, Linear. I'm going to bring the sale amount over as my dependent variable. I'm going to bring these independent variables over, put them in the independent box. I'm going to ask for the ones that are hyperchecked already, and confidence interval, descriptives, collinearity diagnostics. I'm going to leave off Darwin-Watson since we know that these are not autocorrelated data. It's not measured repeatedly over time. We'll look at plots and ask for the predicted on the X, the residual on the Y, histogram, normal probability plot, and partial plots, and then say continue and OK. We can see the descriptives again. We see correlations, which we didn't ask for, but it provides for us. Only one correlation is at all high with baths with square foot home, but it's not problematic, so I don't think we have a multi-collinearity issue. The model summary is important because we're going to look at this adjusted R-square, and we're going to look at the standard error of the estimate. We want the error to go down and the adjusted R to go up as we adjust our model. Right now, we're accounting for about 26% of the variability in the dependent variable with these 4 independent variables. We can see that we have a significant regression, and we can see our coefficients. So we have the constant, which is what the price of the house would be if all of these other things would be 0, which doesn't really make sense. We'll come back to that. We have beds, baths, square foot home, and square foot lot. 2 of these are not significant, but overall with them in the model, we have a significant regression. So we're going to evaluate them in the model. We can see our variance inflation factor is low, so we don't have any multicollinearity. We can see that we have fairly normal. We have this big peak here, but it's fairly normally distributed. And we can see our partial plots. Okay, so we're going to turn to the PowerPoint for a few minutes. Evaluating the output, we want to know, is the linear regression model a good model as a whole? Yes or no? Why or why not? We're going to state the null and the alternate. So the null is that the number of beds, baths, square footage of house, and square footage of lot do not predict the sale price, and the alternate is that they do. Our conclusion, you can see, is f of 344, is equal to 31.3. P is less than 0.01. We can reject the null. The explanatory variables are jointly significant, and we have a useful model. So looking at the model summary, what is the adjusted R-square? So the adjusted R-square for the full model is 25.8. And the adjusted standard error of the estimate is 122,295.19. Evaluating the coefficients, we want to provide the linear regression equation. We look at these betas. These are the slopes. So as we evaluate the number of beds, baths, etc., you multiply by the slope given in the equation. So the constant, when all of these are 0, would be, like I said, 72,837 plus, because this is positive, 111,612 times, and I'm just calling it beds. I could call this x1, x2, x3, x4, but I'm going to use the variable names to make it easier to interpret. Then it's minus, so I have plus, but the negative is here, or I could have just said minus this value times baths, this value times square foot homes, etc. So I want you to go back and look at the first house in your data set and find the values of the numbers of bedrooms, numbers of bathrooms, house square footage, lot square footage, and use those values in your regression equation. What is the predicted value of the sale amount? So I went back to the first record, and that sale amount was $350,000. Plug all these values in, and the predicted value of $224,467.95. So what is the error in the prediction when using this equation to predict the sale amount? So the actual was $350,000 minus this, so I was off by $125,000. So not great. Okay, so model building. Using the output from the full model and the results of the statistical hypothesis testing, which predictor or predictors would you consider dropping from the model? Here we must assess each explanatory variable individually. So we can look, we see that this one, if we look at the significance value, we can see that beds is not, you don't have to worry about the constant, it always stays in the model. Beds is not, baths is not, square foot home and square foot of lot are. So I've written it out. Beds is not a significant predictor. I give the t-value, the p-value, and the confidence intervals, etc. So I would recommend running the model again, removing beds and baths. So based on the results of the full model, run a new reduced model, omitting the predictors that aren't significant, and paste the output, then provide the regression equation for the reduced model. So I've done that. I'm not going to go back and rerun it. It's just rerunning the linear regression and removing those two variables. You can keep everything else the same. So looking at everything here, we can see the adjusted R-square has gone up minimally. The standard error, the estimate, will have gone down a minimal amount, but we're still significant, and now both of these predictors are significant. So our new regression equation, our new constant, is 90,000 plus the 106 times the square foot of home minus this value times the square foot of the lot. Okay, so provide a comparison of the full model with your reduced model. So we're going to look at the full model with our four predictors and our reduced model with our two predictors. And you can see that the adjusted R-square went from 0.2582 to 0.2594. It's increased, but not a whole lot. And our standard error decreased from 95 to 92. So the full model or the reduced model, which is better, we're going to pick the reduced model. It's a better predictor, and it has a higher adjusted R-square and a lower standard error, and fewer variables that provide a better fit is preferred, and it's considered more parsimonious. All right, so let's interpret all the slopes and intercepts to illustrate how the predictors affect the sale amount of a house. So the intercept, though impossible for a house to have 0 square feet and 0 square footage of land, the model indicates that the minimum starting price to purchase a house is $90,000. It doesn't always make sense. Now, this is important. When you're interpreting one of the predictors, you're holding the other one constant. So holding square foot of lot constant. So we're only looking at square footage of home. For every unit increase in a house's square footage, the sales amount increases by 106,000 or 107,000. And then holding square foot of the home constant, for every unit increase in a lot's square footage, the sales amount decreases by $1.35. Okay, so let's try model improvement. The sales amount is sometimes influenced by the age of the house. Create a new variable called age in years based upon the variable build year. Use 2022 as the current year. So we're going to go into transform, compute variable. We're going to call this variable age. Start with the year. You can either use these or just use your keyboard. Minus, bring build year over and say okay. I'm going to write over the variable I've already done. Go to my data and you can see that we have age. I'm going to go to analyze. I'm going to go to descriptives, and this time we'll just use descriptives. And I've already got the age variable in, and just see, you can see here the mean value is 53.5. So go back to the PowerPoint and you can see that I have it here. Okay, so that's how we create that variable. We're now going to run a model with those two variables, the square foot of the home and the square foot of the lot, and we're going to add age. And you can see now that our adjusted R-square has gone up, our standard error of the estimate has gone down. We're still significant, and all of our predictors are significant. So we can check. I just copied this table from the previous slide, and so you can see that we're now substantially improved. We're now lower in the error, and so the model including age is better than the reduced model. This has the highest adjusted R-squared, etc. With this new model, go back to that very first house and try to predict the house price for the first house in the data set. Using the new values, we plug it in and we see that our house price is $240,000. Our first prediction was $224,000, so we're higher, but we're not close to where the actual price was. We're only explaining 33% of the variation that's out there. If you had more variables to use in the model, you might want to test more predictors to see if you could do a better job in the predictive equation, which is why you might consider doing variable selection strategies to optimize the number of variables in your model.